In this video, we're going to have a look at some further gas calculations that will be applied to determining the formula of an unknown hydrocarbon. In our last lesson, we looked at an application of Avogadro's law, which states that equal volumes of gases under the same conditions of temperature and pressure contain the same number of particles. And that leads on to this application, Gay-Lussac's law, that in a reaction between gases, the volumes of the reacting gases, so long as they're at the same temperature and pressure, are in a simple ratio to one another and to the volumes of any gaseous products. In worked example 2 on page 13, we had a look at the equation for propane reacting with oxygen, in other words, the combustion of propane. When a hydrocarbon reacts with oxygen, it produces carbon dioxide, that's the carbon part reacting with oxygen, and it produces water. That's the hydrogen part of the hydrocarbon reacting with oxygen. And what we then do with this equation is we balance it. Okay, the easiest way to balance the combustion of a hydrocarbon equation is to start with the carbon. If we have 3 carbons in the left, we'll need 3 carbon dioxides on the right. Next easiest thing to do is to balance the hydrogens. You can see that we have 8 hydrogens on the left. We have 2 at the minute on the right, and any number I put in front of the water will multiply the number of hydrogens by 2. So you're thinking, what times 2 will give me 8 hydrogens? And that's obviously going to be 4. Then we have a look at our oxygens. We balance that last. If you look at your carbon dioxide, we've got 6 oxygens within that, 3 times by 2. That's added on to the 4 oxygens from water, 4 times 1. So I have a total of 10 oxygens on the right, and I want to balance that on the left. But again, it's O2, so any number I put in front will be multiplied by 2. So what I need to do is put a 5 in front of the oxygen. So that's our balance symbol equation for the combustion of propane. And we can interpret that as 1 mole of propane reacts with 5 moles of oxygen to give 3 moles of carbon dioxide and 4 moles of water. But because of Avogadro's law, which states that essentially 1 mole of any gas at room temperature and pressure occupies a volume of 24 decimeters cubed. So if we have the same number of moles of a gas, it will occupy the same volume. So therefore, if we can read a balance symbol equation in terms of the mole ratio, and if the number of moles is proportional to the volume of gas in a reaction that involves gases, then we can interpret this balance symbol equation in terms of volumes as well. So let me give you an example of that. Say, for example, I started with 100 centimeters cubed of propane. So that's the volume of propane that I start with. Rather than working out the number of moles of that, bringing it over to some other part of the equation and then converting it back to volume, I can just instead use the stoichiometric ratio, the balancing number ratio, with the volume. So that means that if 100 centimeters cubed of propane reacts, and the ratio of propane to oxygen is 1 to 5, then that means it's going to react with 500 centimeters cubed of oxygen. Because all of our products are going to be gases, so oxygen's a gas, propane's a gas, carbon dioxide's obviously a gas, the water is going to in fact be steam at this temperature, because this reaction will be highly exothermic. This is a fuel burning, it's going to release a lot of heat. And so the water produced as such will be in the form of steam. It will be gas as well. So how much carbon dioxide am I going to produce? Well, you can see the balancing number ratio is 1 to 3. So that gives me 300 centimeters cubed of carbon dioxide. And the ratio of propane to water or steam is 1 to 4. So that's going to produce 400 centimeters cubed of steam. So the combustion of hydrocarbons is a really good example and application of Gay-Lussac's law. And it gives us opportunity to work out the volumes of gases that react with each other. And what we can actually use that to do is to determine the formula of an unknown hydrocarbon. And that's what we're going to look at now, starting on page 14. So as I said in the previous slide, Gay-Lussac's law can be used to determine the formula of an unknown hydrocarbon. It's a perfect application of this law. In these types of questions, you'll be given experimental gas volume data from the combustion of an unknown gaseous hydrocarbon and use that to determine its formula. So just before we proceed, I feel like I need to warn you that these questions can sound really complicated. You're given a lot of information in the questions, but you can interpret it. And actually these type of questions, they can't be asked in very many different ways. So it's a sort of thing, once we get our head around it and do lots of practice of it, it will be okay. So don't panic when you see these questions at first, we will get there. So let's have a read through worked example 1 together, and I'm going to highlight some of this information in a few different colours. So if you had a couple of different highlighters, that might help, or coloured pens to underline things, if that sort of colour coding helps you. So we're told that we have 20 centimetres cubed, and I'm highlighting that in one colour, of an unknown hydrocarbon, CXHY. So we don't know the formula of it, that's what we're going to try and work out. It's mixed with, and I'm going to switch colours here, 80 centimetres cubed, which is an excess of oxygen in a graduated tube. Essentially, that's just like a sealed measuring cylinder type thing. It's just a container that has, sort of measurements on the side that we can measure the volumes of the gases. The question then says a spark was applied, so essentially that will get your hydrocarbon reacting with your oxygen. That's all that's there for. So the hydrocarbon reacts with the oxygen, and the resulting mixture of gases was allowed to cool to room temperature. It then tells us that 60 centimetres cubed, and I'm going to highlight that in a different colour, of gas was left. When this gas was exposed to sodium hydroxide solution, the volume fell to 40 centimetres cubed, and I'm going to highlight that in a different colour. It then says determine the formula of this hydrocarbon CXHY, and I'll highlight that in pink again. So those pink highlighting is to do with what we'll use for our hydrocarbon. So there is a lot of information in this question, but it can be interpreted. We are going to be able to work out the formula of our hydrocarbon. First things first is to write a general equation for the combustion of the hydrocarbon. And I know some of this is written in your notes. I'm going to go through it step by step with you. But the balancing is not in there, so you will need to fill that in. So your hydrocarbon has a general formula of CXHY. So a hydrocarbon by definition is just made up of hydrogen and carbon only. You would have learnt that in your organic chemistry at GCSE. So it has X number of carbon atoms and Y number of hydrogen atoms. And so essentially we're using this as an equation to solve for X and Y. So that's going to react with oxygen. We don't know how much oxygen at the minute, but we will balance it generally in a second. When a hydrocarbon reacts with oxygen, as we've said already, it forms carbon dioxide, CO2, and water, H2O. So let's balance this equation. And you might say, well, we can't balance it because we don't know our numbers of carbons and hydrogens, but we're just going to do it in terms of X and Y. So if you remember on the previous slide, I said the easiest thing to do is to balance your carbons first. So let's have a look at your carbons. You have X carbons, so that means I'm going to have X carbon dioxide. So put an X in front of your carbon dioxide. What I said was easiest next is your hydrogens. So if you have a look at your hydrogens there, you have Y atoms of hydrogen, and I have water on the right hand side to balance that with. If you remember, when we were balancing our hydrogens, we said that any number we put in front of our water is going to multiply it by, it's going to be multiplied by 2 because there's 2 atoms of hydrogen in each water molecule. And so to balance this, I don't put Y in front of the water, I put Y over 2. So Y divided by 2. Just to show you really briefly, don't necessarily write this down, but in the last example we were looking at propane. So here we had 8 hydrogen atoms on the left, and we're going to balance that with waters on the right. What number would I put in front of the waters? I would put 4. Why is that? Well, it's because it's 8 divided by 2 gives me 4. So essentially, if I swap that with Y, I would need to put Y over 2. Okay, hopefully that makes sense. Now the oxygen is the most complicated part, so let's have a close look at it. So when we now balance the oxygen, we need to think about how many oxygens we've got on the right hand side. So let's look at carbon dioxide first of all. We've got X multiplied by 2. So how many oxygens we have is 2X. But we also have some oxygens in our water as well. We have Y over 2 times by 1, which is Y over 2. So the total number of oxygens on the right hand side is 2X plus Y over 2. But when I bring that here, you can see that oxygen on the left, any number we put in front of the oxygen, O2, is going to be multiplied by 2. So I can't just put 2x plus y over 2 in front of my O2. I've actually got to divide this by 2. So let's have a think about what that gives me. Divide each one in turn by 2. So 2x divided by 2 is just x, plus we've got y over 2 here. Divide that by 2 and you actually get y over 4. Half divided by 2 is a quarter. Now I know that's a little bit tricky and a bit hard to get your head around, but I wouldn't expect you to be doing this in an exam or to spend your time doing this. I would say try and learn this general balance symbol equation as it is with the balancing numbers in it. So if I take away all of my other writing, if you make sure those balancing numbers are written in, so they're written in purple there, you need to fill those into your notes and make sure you do that really, really carefully. And I would say just learn this general balance symbol equation because that's what you're going to need for all of these types of questions. So maybe put a box around it in your notes, put a big star at it, learn this general balance symbol equation for the general combustion of a hydrocarbon. So just a reminder that all the reactants and all the products in this reaction are gases. We're told in the question, and I'm going to underline some things here, but not in a particular colour, you don't have to do this in your notes. You're told that you've got 20 centimetres cubed of an unknown hydrocarbon mixed with an excess of oxygen. What that means is that all of this hydrocarbon will react and some of the oxygen, but we'll be left with some oxygen in our final mixture. We're also going to be producing gases of carbon dioxide, as we can see from our equation, and steam. It is water, but yes, at this temperature, it's going to be a gas. However, we're told in the question that the gases that are produced are allowed to cool to room temperature. So our hydrocarbon is all used up, and so therefore we'll have oxygen, carbon dioxide and steam. But if the gases are allowed to cool to room temperature, oxygen will stay as a gas, carbon dioxide will stay as a gas, but water will turn into a liquid. And so it will no longer be a gas if it's cooled to room temperature. So actually this next bit of the question, and I would maybe encourage you to write this in, that's 60 centimetres cubed of gas that's left after cooling to room temperature. Water is going to be a liquid, so therefore we're just left with oxygen plus carbon dioxide. So it's the unused oxygen and the carbon dioxide that is produced, because remember the hydrocarbon has all been used up. Water or steam has now condensed to a liquid, so we're left with the unused oxygen and the carbon dioxide. Then you're told in the next part of the question that this gas, as in the unused oxygen and the carbon dioxide, are exposed to sodium hydroxide solution. Now that might sound a wee bit strange. Why are we adding in sodium hydroxide solution? Well, think about it this way, and again, you might want to write this in somewhere. That's an alkali. And what that does is it removes the carbon dioxide. The reason why it does that is essentially as an alkali, it will remove any acidic gases. What you've got in your mixture that is remaining is carbon dioxide and oxygen. Oxygen is a neutral gas. Carbon dioxide is an acidic gas, and so actually it removes the carbon dioxide. So what we're left with after that is just the unused oxygen. So the volume given to you after sodium hydroxide solution is just the unused oxygen. Now you don't have to write all of that in, it is given to you in a couple of paragraphs after the balance symbol equation, but it just might be easy to write it over the question, and you could do this sort of annotation in your exam or in a question. Might also be worthwhile writing down these couple of sentences to summarise what the different information in the question means. So the gas that you're left with after cooling to room temperature, as we said, because that removes the water vapour, the steam, because it condenses back to a liquid. So after cooling to room temperature, you're just left with the unused oxygen and the carbon dioxide gas that's produced. What you'll do is then treat that with sodium hydroxide. That removes the carbon dioxide, so you're left with just the oxygen unused. And from these bits of information, what you can then do is go back or work backwards and work out what the volume of the oxygen used is, because you know how much you added in the first place. In this case, it's your 80 centimetres cubed, and you can take away the volume of oxygen unused. Okay, so now that we've interpreted the question a little bit, and I would encourage you maybe to pause the video if you're not sure, you didn't take all that in. Pause the video, go back and replay it, or have a read at the last paragraph on page 14 and the top paragraph on page 15. But let's fill in the information that we know on page 15. So I've just copied the question over, but this is page 15 that we're now on. So the first thing we need to write down is the volume of our hydrocarbon, and we're told in the question that that is 20 centimetres cubed. It's probably then easiest to go to the volume of oxygen unused, because that's what we find out at the very end of the question. So remember, the gases are allowed to cool to room temperature. That essentially removes the steam out of the situation, out of the mixture, because it condenses to a liquid. So the 60 centimetres cubed we said were the unused oxygen and carbon dioxide. And then we treat it with sodium hydroxide, which removes the carbon dioxide. So that leaves us just with the unused oxygen. So here, that after treating with sodium hydroxide, the volume fell to 40 centimetres cubed. So that's our unused oxygen. Then if we go back and have a look at the carbon dioxide, again, so the volume of the carbon dioxide, well, we know after the gases are allowed to cool to room temperature that we're left with 60 centimetres cubed, and that's unused oxygen plus carbon dioxide. So to work out what is just carbon dioxide, I need to take away the unused oxygen volume. So I have 60 in total, and I'm taking away the 40 centimetres cubed that I know that I have of unused oxygen, and that obviously gives me 20 centimetres cubed. Finally, then we need to work out the volume of oxygen that was used. How do we work that out? Well, what we need to do is essentially the starting volume, our excess volume, and we take away the volume of unused oxygen. So that's going to be our starting volume of oxygen. The excess value was 80, and 40 centimetres cubed were unused. So that gives us a total volume of 40 centimetres cubed that did react. So once we've got the volume of our hydrocarbon that has reacted, the volume of carbon dioxide that we've produced, and the volume of oxygen that is used, then we use these values now with our balance symbol equation for the combustion of the hydrocarbon, and use the ratios of the balancing numbers to get the actual specific values rather than x and y. Once we've solved for x and y, then we know the formula of our hydrocarbon. How are we doing this? Well, essentially this is us applying Gay-Lussac's law that states that the volume of gases in the reaction are in the same ratio as the balancing numbers in the equation for the reaction. So let's go back to our balance symbol equation with our general values of x and y. You may want to write this out again so that you can work underneath it and see where we're getting these values from. And let's write in the values that we've worked out. So we know that 20 centimetres cubed of our hydrocarbon reacted. We know that reacted with 40 centimetres cubed of our oxygen, and that produced 20 centimetres cubed of carbon dioxide. I'm just taking those values from what we wrote just above this part. But just continue on doing your working out on page 15. And just to say, actually, the volume of water or steam doesn't matter. We don't need that. So as we say, an application of Gay-Lussac's law is that these volumes are in ratio to each other, and that ratio will be equivalent to the balancing number ratio. So what we need to do first of all is look at the ratio between the hydrocarbon and our carbon dioxide, because that will allow us to solve for X, and then we can solve for Y afterwards. So solve for X first. So if you just take that part of the equation, ignore the oxygen and water, we've got CXHY as our hydrocarbon, and that's in ratio with X carbon dioxide molecules. As we said, we can use our volumes, our volume ratios, because they will be equivalent to the balancing number ratios. So the volume of hydrocarbon was 20 centimetres cubed. The volume of our carbon dioxide produced is 20 centimetres cubed. So we can see that the ratio between our hydrocarbon and our carbon dioxide is 1 to 1. What does that mean for X? Well, it means that X is 1. And why is that? Well, we can see that our volumes are in ratio of 1 to 1 to each other. That means the balancing numbers are in ratio of 1 to 1 to each other. So if there's essentially a 1 in front of our hydrocarbon, that means there's going to be a 1 in front of our carbon dioxide. So X is equal to 1. So let's now look at the ratio between our hydrocarbon and the oxygen that was used. So you can see from our balance symbol equation that they're in the ratio 1 to X plus Y over 4. So what we'll do is use our volume ratio to get the overall ratio, and then because we know what X is, we will then be able to solve for Y. So we know that we use 20 centimetres cubed of our hydrocarbon and 40 centimetres cubed of oxygen. So that's the volume ratio. And we know that that's equivalent to the balancing number ratio, according to Gay-Lussac's law. So 20 to 40 is the same as, just divide by your smallest number there, is the same as 1 to 2. So the ratio of our hydrocarbon to oxygen is 1 to 2. So that means, because there's essentially a 1 in front of our hydrocarbon, that X plus Y over 4 is equal to 2. I think the easiest thing to do at this point is to multiply everything in the equation by 4. So that would give us 4x, and then because we've got y divided by 4 times by 4 is going to equal y, and that will overall equal 8. So I've just multiplied this first equation by 4 to get that fraction of divided by 4. Or you can follow it through as an algebra equation and do that at a later stage. So what we want to do at this point is solve for y. We know what x is. We know that x is equal to 1. So we are doing 4 times by 1 plus y is equal to 8. So that's obviously 4 plus y is equal to 8. If you bring the 4 over to the other side, you're obviously going to have y equals 8 minus 4. So y is equal to 4. If I just shift that all up a bit so that I can finish writing that off. So we've solved for x and y, and then we just need to think back to what seems like a very long time ago. What was the actual question? The question was determine the formula of the hydrocarbon CXHY. So that means the formula is essentially C1H4 because X is 1 and Y is 4, but we never include 1s in formulas. And so the hydrocarbon is CH4, and you may remember from your GCSE chemistry that that is the alkane methane. So there is an awful lot in that question, a lot of information in the question. And what seems like a lot of working out, but we did that quite slowly, and we'll go through the next ones a little bit more quickly. So feel free to pause and take a bit of a break if you need to. I know these types of questions are quite head melting, so feel free to take a break. But let's have a look then at worked example 2. So I'm going to start you off with this and see if you can finish it off yourself. So I would encourage you to underline these things in different colours if you find that helpful, or highlight them, and just to make a few annotations on the question, and it just makes then your working out a bit easier. So you're told here that you have 20 centimetres cubed of an unknown hydrocarbon CXHY, and that was sparked with 150 centimetres cubed, your excess of your oxygen. When the resulting gases were cooled back to room temperature, you can see this is very similar to the previous question. The volume remaining was 110 centimetres cubed. Exposure of the gases to sodium hydroxide reduced the volume to 30 centimetres cubed. Determine the formula of the hydrocarbon. Okay. So obviously we've got in our question that we reacted it with 150 centimetres cubed of excess oxygen. So that's essentially your used plus your unused oxygen. Okay, then the resulting gases are then going to be oxygen, the unused oxygen, the carbon dioxide and the steam. But when they're cooled back to room temperature, that removes the steam. And so this value of 110 centimetres cubed is your carbon dioxide and your unused oxygen. Then you treat it with sodium hydroxide, and remember that removes your carbon dioxide. And so this value here is just your unused oxygen. So the four values that you'll need to work out is the volume of your hydrocarbon, the volume of the carbon dioxide produced, the volume of unused oxygen and the volume of used oxygen. So what I'd like you to do is to pause the video at this stage and work through each of those volumes and see if you can work them out. Some of them you'll just get straight from the question, some you'll have to work out. So think about the information you've been given and see if you can work out these volume values. So pause the video now, give that a go, and then press play again when you're finished, just to check your answers. So the volume of your hydrocarbon, you get straight from the question as 20 centimetres cubed. Volume of your carbon dioxide then, well, if you look at your yellow and your green value, so it's going to be the difference between the carbon dioxide plus your unused oxygen, which is in green there, and that's 110 centimetres cubed, and that's going to take away, you're going to take away your unused oxygen, which is all that's remaining after it's been treated with sodium hydroxide. So that's 110 minus 30, which is equal to 80 centimetres cubed. The volume of unused oxygen is just straight from the question again, 30 centimetres cubed, because that's all that's remaining after the gases have been treated with sodium hydroxide, as that removes the carbon dioxide. And then the volume of the oxygen used, remember, is just the difference between your starting volume, 150 centimetres cubed, remembering that that was an excess, and you take away the volume that is unused, and the difference between the two is 120 centimetres cubed. So check those values, make sure they're correct before you move on. What you now need to do is write your general balance symbol equation for the combustion of a hydrocarbon. At some stage you will need to learn this. I don't expect you to have learnt it by now, but do try to learn it as you go along here. So there is your general balance symbol equation for the combustion of a hydrocarbon. You will need to write that out and be familiar with the ratios. So what I would do at this stage is write the volumes of the gases that you know underneath the equation. Again, remember, the volume of steam won't matter. We don't need to use that. And what you then go on to do is essentially solve for X and Y using your volume ratios, because those are going to be equivalent to your balancing number ratios. So I'm going to start you off with this and then see if you can finish it off yourself. So the easiest place to start with is to solve for X and then to solve for Y. So solving for X, first of all, you want to put your ratio of your hydrocarbon to your carbon dioxide, because that's going to then be in the ratio of 1 to X when you solve for that. And again, you just use your volumes and that equates to the ratio of your balance symbol numbers. Then what you're going to do is you're going to put your ratio of your hydrocarbon to your oxygen together, and that will give you a balancing number ratio of essentially 1 to X plus Y over 4. And because you've solved for X in the previous step, you can then solve for Y using your simple equation. So pause the video now, give that a go, and then play the video again to check your answer. So the ratio of your volumes of your hydrocarbon to carbon dioxide are 20 to 80. That's equivalent to 1 to 4, so divide both numbers by 20, your smaller number. That gets you in the simplest ratio. And so what that means is that X is equal to 4. So we know that X is equal to 4. We do the same of our hydrocarbon to oxygen, that's the oxygen used, and that is in a ratio of 20 to 120. Simplify that down and you get a ratio of 1 to 6. And what that means is that X plus Y over 4 is equal to 6. So put that into an equation. We know what X is, so we're going to solve for Y. Now you can just put X equal to 4 at this point and sub it in. So one of two ways you can put X in now, that would be 4 plus Y over 4 equals 6. But just be careful, don't multiply the right hand side by 4. At this stage you need to bring your 4 over first of all. So bring that over to the left hand side, it's going to be minus. So it'll be Y over 4 is 6 minus 4, which equals 2. And then you can bring your 4 over to the other side and multiply 2 by 4 is equal to 8. Or as I showed you in the previous example, if you multiply this whole equation by 4, sometimes people find that easier. So instead of X, you'll have 4X instead of Y divided by 4. If you multiply that term by 4, it'll just get you Y. And instead of 6, you'll then get 24. But just make sure you multiply everything by 4. Okay, we know that X is equal to 4, so that's going to be 4 times by 4 plus our Y is equal to 24. That's 16 plus Y is equal to 24. Therefore, Y is 24 minus 16, so Y is equal to 8. So what does that mean for our hydrocarbon? Remember, the question is ultimately asking you, what is the formula of our hydrocarbon? Well, we now know that X is 4, so it's going to be C4, and Y is 8, so it's going to be H8, and that is butene, and that's going to be an alkene. You don't have to name it afterwards, you just need the formula, but that's what it would be equivalent to. So I am quite positive that I have completely fried your head. So I'm going to leave it there for now. If you want, you can go back and go over some of those examples. I would actually really encourage you to try those 2 examples again on file paper without your notes and see if you can do it completely by yourself. I think that would be really good practice. The other thing you could do is to start exercise 5, which is on page 18, but there's no pressure to do that today. I'm going to give you time on your Tuesday or Wednesday lesson of next week to do that. You'll also see there's worked example 3 there, but it's a little bit different in how we do the working out of that, so we'll leave that for our next lesson. So you can go over there and try the examples we've done so far again, and to give you a bit of practice. You can make a start on exercise 5 if you want, but we are going to come back to these on your Tuesday or Wednesday lesson, so feel free to leave it there for now. Thanks for sticking with me. Hope I haven't fried your head too much, and please let me know if you have any questions.